All right, how is everybody doing today? We're going to look at quadratic problem solving, specifically instances where we're going to end up with a quadratic equation to solve or to analyze that comes from the paragraph. So at some form or another, we're going to see quadratic equations in all of the work we'll do for the next couple of weeks. What we have to learn to do is to develop strategies to take complicated problems and make them easier to understand. So for this particular set, I'm going to show you some of the three different strategies that I like to use. And one of them is making a table. If you got a description, you can sometimes make a table and you can get a better sense of what's going on with the data. So that's what we'll look at first. In this case, I guess the second strategy was if there's any geometry problems, you definitely got to draw a picture and study the geometry and look at the shapes and figure out how the shapes are interrelated. So in this first case, what we have is the length of a rectangular garden is 5 feet longer than the width. So that's one given fact. And this is the area of the garden is 300 square feet. Find the length and the width. So that's all we know. So I know something about these three things. I know something about width, I know something about length, and I know something about area. So what I'm going to do is I'm going to explore the length, the width, and the areas, understanding, of course, that we multiply the length times the width, that gives us the area. I wonder why that is. I arbitrarily chose width to be 10 feet long, and then the length had to be 5 feet longer, so 10 by 15 gives us a total area of 150. Now we need an area of 300, so just by guessing I am too short, too small of a garden. So I double the x and make that 20. 20, that means length has to be 5 longer, that's 25, and that gives me a total of 500 square feet, which is too big. So clearly my value that I'm looking for is going to be somewhere between 10 and 20 feet. So one of the things that's nice about doing this table with the geometry is I know where my answer is now going to be, but it also helps me develop, generally speaking. If I let the width be w, then the length would be 5 more than w. That's w plus 5. And to figure out the area, we just multiply w times w plus 5. Gives us a total area. So here's an equation, and it happens to be quadratic. And I think that says sine, but what it was supposed to say is since. So let's put the e down. Since a equals 300, 300 equals w squared plus 5w, and that is a nice, easy factorable equation. And it proves that the width could be either 15 or negative 20. We can't have a negative 20 width, so we want the width to be 15. Logically speaking, if the width is 15 feet, then the length would have to be 20 feet, and then we would get an area of 300 square feet, because 20 times 15 equals 300. So, really straightforward problem that was very simple. Now, many students would be able to just write the equation w times w plus 5 equals 300, and they wouldn't need to go through all this rigmarole. But what we want to do is, for easy problems, we want to learn how we can unpack the problem so that when we get to the more challenging problems, we will have the tools in place. Here's an example of a more challenging problem because there's a lot of stuff going on. What we have basically is a bunch of things. We have the length, the width, the cost, and the area. Now, how did I get length, width, and cost and area out of reading these variables? It's simply a matter of just reading the problem and looking for things that they describe that seem to change. Now, the cost per foot is a rate. That's a rate, not a cost. So remember that. A rate is not one of my variables here, but we have a fixed cost of $5 per foot, and we have a fixed rate of $3 per foot, depending on whether we're dealing with expensive fencing or cheaper fencing. Anyway, these are the things that I don't know. I don't know the length of the width of the rectangular pen. I don't know the total cost, and I don't know the area. But those are all things that have to play in, because it says the area has to be 1,200 square feet, and it says we need to find a function that talks about the cost and everything else. So here's what I'm going to do to try to understand the problem a little better. Again, defining all of my variables, I'm just going to look at cost. And to figure out cost, all we have to do, figure out cost in dollars, is to figure out the rate of price times the length, and that'll give us the cost. So $3 per foot times x plus y feet. Where did I get that? Well, there's x plus y plus y. So all three of those sides together are going to get the total length that's going to cost $3 per foot. I'm going to pay an additional $5 per foot for the x on the other side. That's the expensive side. So if I simplify this, I get 3x plus 6y plus 5x, or 8x plus 6y. So this is my function for cost. However, the cost function has too many variables in it. There's an x variable and a y variable. That's when I get to another statement which says the garden is to have an area of 1,200 square feet. So if the garden is 1,200 square feet, we now have a way to express x and y, because if x was 100, then y would have to be 12. If x was 2, then y would have to be 600. They're tied together. So to make that relationship more explicit, I solve for y by dividing both sides by x, and I get y equals 1,200 over x. That enables me to take my cost equation, and wherever I saw y, I replace it with x. Simplifies out to be the cost is 8 times x plus 7,200 divided by x. So what that means is I can choose how long the fenced-in side is along the highway. I pick whatever I want, and whatever I choose the length to be, I just put and multiply by 8, and then I add 720 or 7,200 divided by that same x value, and that will equal my total cost. To make sure that that is valid, or not valid, what we know is in part B, we have $500 of money to spend. This should be 500, not 400. So if the cost was 500, put the 500 in here and solve. As is, it does not look very much like a quadratic equation. However, I see a variable in the denominator, and if I would like to fraction bust to make it go away, just multiply both sides by x. And that's starting to look really quadratic. So I'm just going to make everything look a little nicer, a little cosmetics for us. I divided everything by 8, first of all. Made everything look quadratic, and then just to get rid of the fractions, I multiplied both sides by 2. I can do that because this is equal to 0. You could double everything, all the coefficients, if the right-hand side is equal to 0, because 0 twice is the same thing. This turns out to be a factorable equation as well, so I factor, and I solve, and I get two viable solutions. Either x could be 40 or x could be 22.5 feet. So option A, we have a 40 by 30 garden. Now a 40 by 30 garden, 40 times 30 equals 1,200, so it already meets the area requirement. Now I just need to see if it matches the cost requirement. 8 times 40 plus 6 times 30, $500. So this is one way I could build it. We go with a 40 by 30 rectangle. Option B, we could make x equal 22.5. That would make the y longer. We get a rectangle that looks kind of like that, and then we would just have to get the cost. 8 times 22.5 plus 6 times 53 1/3 does equal 500 as well. So there's two ways to get 1,200 square feet with $500 in cost, and it's by either making a rectangle 40 by 30 or by making the rectangle 22.5 by 53 1/3. Finally, the last problem, we should take the equation. Remember, it was 8x plus 7,200 over x equals 500. We could find the intersections and see that they match, just to make sure I did the algebra right. Finally, we get into this last question. We're going to do this real easy. Basically, we're going to cut a wire into two pieces, and then fold those pieces into squares, and we're going to add the area of the squares. For example, if I chose x to be 4, I'm going to have 4, and then the other 6 centimeters for a total of 10 centimeters, 4 by 6. The 4 is folded into 4 equal parts, so we have 1 on each side. The 6 is folded into 4 equal parts, so we have 1.5 on each side. Find the area of the first square. It's 1 times 1. Second square is 3/2 times 3/2, for a grand total of an area of 3 1/4 square centimeters. If I chose x to be 2, I would have a small wire and a much bigger wire, which this one can be cut into quarters, so each side is going to be 1/2 long. The 8 is going to be cut into quarters, so each side is going to be 2 long. The area is going to be 1/2 squared plus 2 squared, which is 4 1/4. Now, the whole purpose of doing this is not to solve the problem itself, but to understand the nature of the variables and how they relate to one another. Then if you do this with a couple of fixed examples just to understand the problem, you can create an algorithm. Step 1, choose a value of x. The other side is going to be 10 minus x. Step 2, divide each side into 4 equal parts. That's to make the squares. 3, square each quarter. That is to find the area of both squares and add them together. So really, there's not much to this problem. If I follow the algorithm in general, I choose all my sides to be x. The other one is 10 minus x. I'm going to divide each side into 4 equal parts to turn them into squares, and then I'm going to square each of those quarters so that I can add them together to get the total area. So first, I make x and 10 minus x, and then I cut them into 4 equal parts. That's how I divide them by 4, and square them both. Just to make it cosmetically more appealing, I'm going to follow through with the squaring process, divide everything by 16, and get the following quadratic equation. Just to make sure that the equation is valid, I remember in the earlier slide I made x equal to 4. If I put 4 in for x, I'm going to get a grand total of 3 1/4, which is consistent with the work I did in the last slide. Feel free to check it out. Anyway, to find the maximum, which is the other question, the value of x that minimizes the total area, sorry, I said maximize, my bad. But if we let x equal negative b over 2a, we're going to get 5 centimeters. So in other words, if we cut the wire in half, we're going to get the smallest area between those two wires. So I hope that's helpful. Have a great day.